Hi everyone, my name is Abhinay Kumar Reddy and today I will be presenting Beyond Surveys real-time user satisfaction prediction with LLMs and telemetry. This model, real-time net promoter score prediction using a multi-model AI, aims to address one of the most persistent challenges in customer experience analytics, the inability to capture timely and unbiased user sentiment at scale. Dynamic Net Promoter Score model leverages behavioral data, telemetry signals, and text analytics to predict Net Promoter Score in real time with significantly higher accuracy than traditional approaches. Let's see what is Net Promoter Score. Net Promoter Score or NPS is widely regarded as the industry standard metric for measuring customer loyalty. It is based on a simple question: how likely are you to recommend us? Users respond on a 0 to 10 scale, and their responses are categorized into detractors, passives, and promoters. Despite its simplicity, NPS remains one of the most influential metrics in product organizations, guiding strategy, customer satisfaction initiatives, and growth forecasting. Let's see how NPS is calculated. As you see here, detractors are the one who provided the rating of 0 to 6 out of 10, and passives 7 to 8, and promoters 9 to 10. And NPS is calculated using the percentage of promoters and detractors. It is calculated by subtracting the percentage of detractors from the percentage of promoters. NPS ranges from -100 to 100. Scales below 0 indicate poor customer sentiment, while scales between 1 and 30 are considered good. Scales between 31 and 70 shows a strong market position of the product, and anything above 70 is considered world-class. This framework has been adopted globally due to its simplicity, but I'll show later it also comes with significant limitations. Let's see how companies collect NPS today. Currently, NPS data is collected mostly through email surveys, in-app pop-ups, SMS surveys, and more manual follow-ups. These methods rely heavily on active user participation. They are slow, disruptive to the user experience, and often provide stale information, sometimes collected days or even weeks or even months after the actual interaction. While these tools have become standard practice, they fail to reflect real-time user sentiment. The next slide, we'll see what the companies are facing problem with the NPS. There are four major challenges common in traditional NPS collection. First is the participation gap. Response rates generally fall between 1 and 5%, which means majority of the users remain silent. So less than 5% of users respond to our surveys. Second is the speed barrier. Insights become available only after a significant delay. The results suffer from severe response bias because only extremely positive or extremely negative users tend to answer surveys. And it is reactive. By the time a team receives the NPS score, the opportunity to fix the issue has already passed. So we have the low response rates, stale data, vocal bias responses, which results in lost customers, no visibility, and slow response, which in turn results in the millions in lost revenue for the companies. This leads to us to an important question. What if we could eliminate surveys altogether? What if we could calculate user sentiment instantly without requiring any form of user input? What if we could reliably predict Net Promoter Score in real time? This forms the foundation for our work: predictive multi-model NPS estimation. Introducing DNPS, Dynamic Net Promoter Score. Let's see what is DNPS. DNPS predicts user sentiment using a combination of telemetry data, behavioral analytics, session patterns, and machine learning. The goal is to produce a reliable, continuously updated sentiment score for every user session without requiring survey participation. This approach allows organizations to transition from reactive measurement to proactive sentiment prediction. As you see here, we have different layers for the DNPS model: data ingestion, AI prediction engine, and real-time insights. Let's see what each layer do. So first one is the data collection layer. To achieve accurate predictions, DNPS relies on three key categories of data. First, behavioral interaction data, which captures how users navigate and interact with the system. Second, telemetry and system signals, which provide insights into the performance of the platform during each session. Third, user feedback and textual inputs, which include explicit comments, support messages, and survey responses. These multimodal signals enable a more holistic understanding of user sentiment. Some of the examples of behavior interaction data are click patterns and navigation flows, session duration, dwell time, event error events and drop-offs, future usage sequences, and telemetry and system signals, event logs from backend services, performance metrics, device application metadata, user feedback and textual inputs, in-app survey comments, and chart agent transcripts. So once the data is collected, it provides to the next layer, data processing layer. Data processing layer consists of data cleaning, normalization and structuring, timestamp alignment, future extraction, data storage staging. Our pipeline begins with data cleaning to remove noise, duplicates, and incomplete entries. We then perform normalization and structuring to convert raw session data into consistent formats. Timestamp alignment is critical since events from multi sources must be ordered accurately. Next, we extract future key features, including statistical metrics, behavioral patterns, and text embeddings. Processed data is stored in a staging layer, which supports both offline training and real-time predictions. Let's go to the next layer, hybrid AI modeling. Our DNPS architecture uses hybrid multi-model structure designed to handle structured metrics, sequential behavior, and text data. Each model type specializes in a different modality and contributes unique insights into the final prediction. The fusion of these models ensures higher predictive accuracy than any single model could achieve alone. Additionally, this structure supports explainability, enabling us to assess the contributions of each input feature. See here, all the models calculate and provide it to the fusion layer, and fusion layer combines all the model scores and provides the final NPS score. Let's see each model in detail. The hybrid model is composed of three core components. First, a structured data model implemented using gradient boosted decision trees such as XGBoost or LightGPM, which excels in capturing nonlinear patterns in behavioral and telemetry metrics. Second, a temporal sequence model implemented using LSTM or transformer architectures, which learns user behavioral trends across time. A text model using BERT-based embeddings, which captures sentiment, semantics, and topical relevance from user-generated text. Together, these models provide a multi-dimensional representation of sentiment. Let's talk about the fusion layer. Fusion layer combines outputs from all three models into a single prediction. Rather than treating each model equally, it learns to weight each one depending on its predictive importance. This selective weighing ensures that the most relevant signals, whether behavior, performance related, or textual, dominate the final NPS estimation. The fusion layer has the explainable AI to ensure transparency and interpretability. We apply post hoc explainability methods such as SHAP and LLM. These methods allow us to analyze how each feature influences the predicted NPS. Explainability is essential for trust and adoption, especially in operational environments where business leaders need to understand why a model generates a particular prediction. See here, clarifies why a prediction was made, uses SHAP and LLM, improves trust and transparency, helps with debugging and validation, supports compliance and audit needs. The XAS increases confidence by showing how and why prediction was made. Final layer produces the final dynamic NPS score, provides the confidence level of the prediction and shows root cause factors affecting the score, suggests actionable recommendations, and delivers insights to business dashboards. Let's talk about the prediction results and model performance. DNPS model achieved an accuracy of approximately 85.9%, outperforming all models evaluated. The model produced a low mean absolute error of around 1.21 and demonstrated strong F1 scores across promoter, passive, and detractor in categories. Application study is performed and shows that removing text data reduces accuracy to around 55%, while removing behavioral and telemetry data results in a drop to about 78%. As you see in this chart, removing each one like no text, no structured, text only, and structured only drops the accuracy of the percentage of the model. Real-time inference latency is roughly 80 milliseconds, which makes the system viable for live dashboards and operational workflows. Explainability and insights and business value. Explainability analysis reveals several key drivers of NPS. High backclick frequency strongly correlates with negative sentiment. Short session durations often indicate dissatisfaction. Higher intentional click activity tends to correlate with promoter behavior. These insights help product and engineering teams identify root causes such as UI friction, system buffering, or negative feedback patterns. From a business perspective, DNPS enables proactive decision making, reduces reliance on surveys, and produces real-time sentiment intelligence across customer journey. Let's talk about the limitations and future work. Despite its advantages, the DNPS approach has several limitations. It requires access to large, high-quality datasets, and performance may degrade in cold start scenarios involving new users. Model complexity introduces operational overhead, and text-based signals can introduce bias. For future work, we intend to explore more diverse data sources, incorporate advanced transformer architectures, improve cold start handling, and enhance real-time explainability. These improvements will support broader adoption and even more reliable NPS predictions. Thank you. If you have any questions, please reach out to me on LinkedIn. Thank you.